So this video continues looking at the electronic structure of an atom. So these are the energy levels that your textbook shows. So energy level 1, and then we have energy level 2. So this here is energy level 1, and then this is energy level 2. Energy level 3 is right there. Now energy level 4 consists of 4s, 3d, and 4p. So notice the D energy level, the 3D is too high to remain in the actual energy level 3. So it's filtered, it's moved in to energy level 4. And that makes sense because look here, this 3D level 4, you have 10 more electrons sitting there. And if you go all the way up here, here is level 1, 2, 3, and 4. So notice these are the 10 electrons we're now referring to. This is the 3D. Okay, so that's why they're one level. They're always staggered. So it's not 4D, it's actually 3D because they're from energy level 3, but there's no electrons there for those for them to occupy any space there. So that's how that works. And then energy level 5 is going to be 5s, 4d, 5p. Energy level 6 is 6s, 4f, right? They're coming from the s, p, d, and f. 5d, 6p. And then this is energy level 7 at the very end there. So if you were to write this pattern out, you would get 1s, 2s, 2p, 3s, 3p, 4s, and then 3d is lower, and then 4p. And that's what you find when I give you this energy setup here. So here's energy level 1, okay? Here's energy level 2, here's energy level 3, and then there's energy level 4. Okay, so I have them written exactly based on the lowest energy level coming first. And then energy level 5 is 5s, 4d, 5p, and that's what you see right here, 5s, 4d, 5p. And then we go on to 6s. Now, before we can get to 6p, there's a lower energy level 5d, but before we can get to that, there's 4f, and then 5d, and then 6p. And that's what you find right here. So you find 6s, 4f, 5d, 6p. And then the last one is 7s, 5f, 6d, 7p. Now you don't have to memorize any of these. You will always be given one of these charts. And this is just another example here of the Bohr's model. So the Bohr shells here, 1 to 7, the maximum number of electrons, 2 to 23 or 32. And then we have Schrodinger's model on top where you have the S, the D, the P, and the F. Just a couple of things I wanted to go over here with some terms. So a closed shell is when no more electrons can fill that orbit. So all noble gases have closed shells. They're very stable. So like neon here has the maximum 6 plus 2, 8 electrons in its outer shell plus 2 in the core. Open shells, so closed shell atoms are non-reactive with the other elements. They don't need to give or take electrons to become stable because they already are stable. So their charge is always 0. Open shell atoms, on the other hand, would be all the other elements on the periodic table. They need to give up or take electrons to become more stable. So when they give up an electron, they become more positive and they're called cations. And when they take electrons, they become more negative and they're simply called anions. But both of these fall under the category of ions, and we can better specify them as cations or anions depending on if they're positive or they're negative. Okay. So just a quick thing here. So how many electrons do each of the following have? So if you look at lithium, if this is written in standard notation, you'd have like the mass number up at the top here in this corner. So here the number of electrons in lithium would be 3, beryllium has 4, and then we've got 5 for boron, 6 for carbon, and 11 for sodium. Now core notation, we looked at electron configuration in the other video, and we found that it takes a really long time to write out the electron configuration for some of the elements. Like something like lithium is simply 1s2, 2s1. So there's the 3 electrons right there. Something like sodium would be 1s2, 2s2, 2p6, and then 3s1. So it took a while to write that out. So instead of taking all that time to write this out, there is a shortcut called core notation. Core notation simply involves taking the atom or the noble gas from the previous level and using it to replace the inner shells of the complete electron configuration. So if we're looking for a noble gas, we're looking for a P6 configuration. If we have a P6 configuration, then we have a noble gas and we can find it. So here we have 2P6. So that is going to correspond to neon. So this entire configuration right here corresponds to neon. So what we're going to do is put that in square brackets and then have the overflow electrons written out like that. And this, therefore, is the core notation for sodium. So neon has up to 10 electrons, 6 plus 2 and 2. That's 10. And then we have that one extra electron to make up sodium. So that would be our answer for this one here. So let's look at lithium, for example. We'll just do this one here, 1s2, 2s1. So core notation involves the noble gas one level above. Now this is an exception. When you're looking at level 2 elements, you can use an S2 configuration, which represents helium. So here, this is helium. So that's one level above. That's the only exception here. And then 2s1. Okay. For phosphorus, now this is a good one because this one is quite the configuration. 1s2, 2s2, 2p6, 3s2, and then 3p, 1, 2, and 3. So what we're doing is we're looking for a P6 configuration, and here it is. And once again, that represents neon, so we're going to bracket that off. And then all of the extra electrons, or the valence electrons as we call them, would be written out. So these are your core electrons, and these are your valence electrons. Okay, so valence electrons are the electrons in the outer shell. So here we have our valence electrons. Core electrons are not involved in reactions. They are non-reactive. They're happy. They're stable. So if we're writing the core notation for ions, what we want to do is for a negative ion, you simply have to make sure that you add electrons to the last shell. Okay, and for a positive ion, you have to remember to remove electrons to make the overall charge more positive. Okay, so if we're looking at, and what we can do here is, I can actually write this one out. So if we're looking at arsenic, we can write out its core notation. It's argon, and then it's 4s2, 3d10, 4p3. So we want to actually create arsenic -3. So we want a charge. So we want a -3 charge. So what we have to do is we have to remove 3 electrons from that outer shell. No, sorry, we have to add 3 electrons because we're making it more negative. So when we add those 3 electrons, we're going to give this a -3 charge because we've added 3 negatives. And then we can rewrite this as P6. And notice we have a P6 configuration. So we have now created, in a sense, a noble gas, so like krypton. So that's what we have. So that's the whole point of ions. You're trying to add or take away electrons to make the atom look like a noble gas. So once you've done that, then you know that you have added electrons or taken them away properly. So if we're looking at nickel, for example, now the transition metals are a little bit tricky. So let's maybe look at something like magnesium. So the core notation for magnesium would be one level above, so that would be neon, and then 3s2. So we want to make magnesium have a stable configuration. So we want to get rid of those valence electrons. So either we can add 6 more electrons or we can take away 2. So taking away 2 electrons is a lot more easier. So we take away 2 electrons. So we're left with 0. So then we're left with a charge of +2. So if we take those away, this whole shell is gone. And now we're left with simply neon. So that's how ions work. You either take electrons away, as in the case of magnesium +2, or you add electrons to get a noble gas configuration. Just a quick note, electrons in the outermost shells are removed first. Electrons are removed from p, s, then d orbitals. You don't want to take away from d orbitals. Okay, they are considered more stable if you have a full d shell. The outer electrons are called the valence electrons, and they are ones that take part in reactions, do not include core or filled D or F subshells. So this is beyond the scope of this course, so we're not going to go into that. A few exceptions are the D4 and D9. They are not considered stable orbitals, so you have to make sure when you write the electron configuration for them, you borrow from the s orbital before it. Okay, that's just an exception, that's a rule. So here we have chromium. Has a 4s2 3d4 configuration. Now notice it's a D4. This is what you have to recognize. It's a D4 shell, and that is not stable, so we have to borrow. So what we're going to do is we're going to take an electron away from here and add it to the D5. So we're going to take an electron away from the S. So what we're left with is argon 4s1 3d5. And that's the configuration for chromium. Okay, so D5, D5, and D10 are stable. So even if we can get a half-filled D shell, that's more stable than like a D1, 2, 3, or 4. Okay, so we have to try to get a D5 if we can, and this rule only works for D4 and D9. That's what the chemists have found. So here, if we want to, we've got a D9. You have to recognize you've got a D9, so you don't want to write that as your configuration. Remember to borrow -1 +1. So what you're left with for copper is argon 4s1 3d10. And this applies to all the D4s and all the D9s. So a filled D subshell is considered stable, and so is a half-filled D subshell. This rule can also apply to a F14 and F7. Okay, so if you have an F6 or an F13, make them completely full or half full, and then that would be considered stable.